Good afternoon and welcome to Lecture 7. This week I'm going to talk about rank and nullity, the fundamental matrix spaces, linear transformations, composition and inverse transformations, and finally isomorphisms. First, let's talk about rank and nullity of a matrix. Now, recall that if we're trying to find the row space of a matrix A, what we do is we reduce it to REF, row echelon form, and then we take the rows with a pivot. For example, the matrix A is row equivalent to the matrix R, and the matrix R has 3 pivots. First row, the second row, and the third row have a pivot in them. So these are the rows we take. We take row 1 of capital R, row 2 of capital R, and row 3 of capital R. This gives us a basis for the row space of R, but because row space is not changed by the elementary row operations, that's also a basis for the row space of A. Because this basis has 3 elements, and it has 3 elements because R has 3 pivots, that means that the dimension of A is equal to 3. The dimension of the row space of A is 3. The dimension of the row space of A is the same as the number of pivots in R. And let me also remind you that if we want to find a basis for the column space of A, then we take the pivot columns. R has a pivot in the first, third, and fifth columns. So we go back to looking at A and we take the first, third, and fifth columns. This gives us a basis for the column space of A. Because we have 3 vectors in our basis, that means that the dimension of the column space of A is 3. So again, because we have 3 pivots, that tells us that the dimension of the column space of A is 3. So of course, the row space of A is 3-dimensional and the column space of A is 3, both because we have 3 pivots in capital R. And that's always going to be true. The row space of a matrix and the column space of a matrix will always have the same dimension. Why? Because the dimension is just number of pivots in the row echelon form of the matrix. And this is an important number. The dimension of the column space of A, which is the same as the dimension of the row space of A, is called the rank of A. And the nullity of A, we had one more space last week to talk about. The nullity of A is the dimension of the null space of A. So, for example, find the rank and nullity of this matrix. The first thing we need to do is we need to row reduce this matrix. And I'm just going to tell you that matrix A is row equivalent to this RREF matrix. And I'm leaving that for you to check. For the time being, just believe that this is true. Capital R has 2 pivots. That means the row space of A is 2-dimensional and the column space of A is 2-dimensional. So we can say that the rank of A is equal to 2. To find the nullity of A, we need to find the dimension of the null space of A. In other words, we need to find the dimension of the solution space of AX equal to 0. From capital R, we can imagine that we have an extra column of zeros here in an augmented matrix. We can see that we have 2 basic variables and 1, 2, 3, 4, 3 variables. x3, x4, x5, and x6 are our free variables, and then x1 and x2 are given in terms of x3, x4, x5, and x6. Or in vector form, what we can do is we can say, we'll put x3 is 1 and put the other one 0. So that's 1, 0, 0, 0. So x1 must be 4. And then in the second equation, x3 is 1 and the other one's a 0. So x2 must be 2. And then do that the same thing, but with x4 is 1 and the others are 0, and then the same thing with x5 is 1, and so on. We find that we can write the general solution to the homogeneous system like this. It's a linear combination of 4 vectors. And just from looking at the bottom 4, that's just a basis for R4. So clearly these 4 vectors are linearly independent. So that means that we have a basis for the null space of A. This basis for the null space of A contains 4 vectors, so the null space of A is 4-dimensional. The nullity of A, which is the dimension of the null space, is therefore 4. 1, 2, 3, 4. Now, note, rank A is the number of pivot positions. The pivot positions correspond to the basic variables. And the nullity of A is the number of free variables. But if we do number of basic variables plus number of free variables, then we get the total number of variables. In other words, we get the number of columns of the matrix A. And this is an important theorem, something that's going to be important for you to remember for the second exam, I would imagine. If A is an m by n matrix, in other words, a matrix which has n columns, then the rank of A plus the nullity of A is equal to n. For the second exam and the final exam, make sure that you remember this formula. Not every year, but most years, there's a question involving this formula. So, for example, the matrix we just looked at has 6 columns. The rank was 2, the nullity was 4, and 2 plus 4 is equal to 6. So, let me ask you 2 questions, and these are about the formula in the yellow box at the top. The rank of A plus the nullity of A is equal to the number of columns of A. Suppose that A is a 5 by 7 matrix of rank 3. Find the nullity of A. Okay, we have 3 people saying 2, 3 people saying 3, and 5 people saying 4. I can tell you that the correct answer is 4. The number of columns of a 5 by 7 matrix is 7. We're told that the rank is 3, and then we're asked to find the nullity. So 3 plus what is equal to 7? The answer is 4. Let's do another one. Suppose that the solution space of Bx equal to 0 is two-dimensional. If B is a 5 by 7 matrix, find the rank of B. Five people voted for 2. 5 people said the rank of B is 5. 1 person said the rank of B is 6, and 2 people said that the rank of B is 7. The answer is that the rank of B is equal to 5, because this matrix has 7 columns. We're told that the solution space of Bx equal to 0 is 2. In other words, the null space is two-dimensional, so the nullity is 2, and therefore the rank must be 5. If we have a non-homogeneous linear system, Ax equal to B, and if we know that this is a consistent linear system of m equations in n unknowns, so in other words, if A is an m by n matrix, and if we know that A has rank R, so there are basic variables, then the general solution has n minus R free variables. Number of columns minus the rank tells us the number of free variables. Our next topic for this week's lesson is the fundamental matrix spaces. Have a look at these 6 vector spaces: the row space of A, the column space of A, the null space of A, the row space of A transpose, the column space of A transpose, and the null space of A transpose. Now remember, what do we do when we take the transpose of a matrix? What we do is we swap rows to columns, and columns become rows. So that means that basically the row space of A is the same as the column space of A transpose. And the column space of A is basically the same as the row space of A transpose. Columns become rows, rows become columns. So we can, instead of 6 different spaces here, we have 4 different vector spaces. And these 4 different vector spaces are called the fundamental spaces of matrix A. That's the row space of A, the column space of A, the null space of A, and the null space of A transpose. We're going to be talking talking about these four vector spaces and how they are related. My first theorem says if A is any matrix, then the rank of A is the same as the rank of A transpose. And I want to prove this. And we can prove it like this. The rank of A is the dimension of the row space of A. But the row space of A is just the same as the column space of A transpose, because when we do transpose, rows become columns and columns become rows. But the dimension of the column space of A transpose is just the rank of A transpose. So that was a nice simple proof. If A is an m by n matrix, m rows and n columns, then A transpose is going to be an n by m matrix, n rows and m columns. So using the formula from the last section, the rank of A transpose plus the nullity of A transpose is equal to the number of columns in A transpose, which is m. If the rank of A is R, that means the dimension of row space of A is R, and by the previous theorem, the dimension of the null space of A, the nullity of A, is number of columns minus the rank, n minus R. The dimension of the column space of A is also going to be R, also the rank of A. And then using the formula which I've just said, the dimension of the null space of A transpose is going to be m minus R. Now suppose that X is a solution to this linear system. Let's look at the first zero. How do we get that? What's the first equation? The first equation is going to be 1x1 plus 3x2 and so on. Basically, the first line is just going to be this green vector dot this orange row vector. Or in terms of matrices, we can do this green row vector multiplied by this orange column vector. And that's going to be equal to this 0. So that tells us that if the vector x solves ax equal to 0, then x is orthogonal. Orthogonal means the dot product is equal to 0. Is orthogonal to the first row vector. But of course, we could do this for any row. Similarly, row 2 dot product x is going to be 0. So x is orthogonal to row 2, x is orthogonal to row 3, and x is orthogonal to row 4. Let's write this idea as a theorem. If A is an m by n matrix, then the null space of A, in other words, the solution space of Ax equal to 0, consists of all the vectors in Rn that are orthogonal to every row vector of A. We need some sort of notation for a space of vectors which are orthogonal to another set of vectors. Let's suppose W is a subspace of Rn. Then the set of all vectors in Rn that are orthogonal to every vector in W is called the orthogonal complement of W, and we denote it with this symbol, W to the power and then an upside down T if you wish. So in other words, the orthogonal complement of W is all of the vectors V in the vector space, here vector space is Rn, such that V is orthogonal to W for all W in capital W. And if W is a subspace of Rn, then we can say that the orthogonal complement of W is also a subspace of Rn. W intersection with its orthogonal complement is the set containing only the zero vector. And number 3, the orthogonal complement of W is just W. Let me show you some examples of orthogonal complements. Let's suppose our vector space is R2, and let's suppose our subspace W is a line passing through the origin. Then the orthogonal complement of W is going to be the vectors which are orthogonal to this line, or perpendicular to this line. So we have another line passing through the origin where the angle between them is 90 degrees. Or let's suppose our vector space is R3, and let's suppose our subspace W is a plane passing through the origin. Then the orthogonal complement of W, all of the vectors which are orthogonal to this plane, is going to be this line passing through the origin. Or one more example. If our subspace W is a line passing through the origin, then its orthogonal complement, so all of the vectors which are orthogonal to this line, is going to look like this. It's going to be a plane passing through the origin, which is normal to or orthogonal to the line. Now, note that the orthogonal complement of a vector space V is just the set containing the zero vector. Why? Because only the zero vector is orthogonal to every vector in V. And then if we take the orthogonal complement of both sides, like this, then of course the orthogonal complement of the set containing just the zero vector is the whole vector space V. Let A be an m by n matrix, then the null space of A is the orthogonal complement of the row space of A in Rn. The null space of A is the orthogonal complement of row space of A, or taking the orthogonal complement of both sides, we could say that the row space of A is the orthogonal complement of the null space of A. Because when we do the transpose, rows become columns and columns become rows, we can also say that the null space of A transpose is the orthogonal complement of the column space of A in Rm. Null space of A transpose is the orthogonal complement of the column space of A, and that's the same as saying that the column space of A is the orthogonal complement of the null space of A transpose. So that is how these fundamental matrix spaces are related. Now I have a big theorem with 17 statements. Let A be an n by n matrix, so that's a square matrix. The following 17 statements are equivalent. Some of these we've seen already. Statement 1, A is invertible. A is invertible if and only if AX equal to 0 has only the trivial solution. And that's true if and only if the reduced row echelon form of A is the identity matrix. That's true if and only if A is expressible as a product of elementary matrices. That's true if and only if AX equal to B is consistent for every n by n matrix or vector B. AX equal to B has exactly one solution for every n by 1 matrix B or every vector B. And that's true if and only if the determinant of A is not equal to 0. These we've seen before. Let's reveal some more statements. This is true, so A is invertible, the determinant of A is not 0, etc., etc. These are all true if and only if the column vectors of A are linearly independent, the row vectors of A are linearly independent, the column vectors of A span Rn, the row vectors of A span Rn, the column vectors of A form a basis for Rn, the row vectors of A form a basis for Rn. And that's true if and only if the rank of A is n. So that's n by n matrix, rank of A is equal to n. So we have n pivot positions. So in other words, the reduced row echelon form of A is the identity matrix. That's how we know we have n pivots. Remember, rank plus nullity is equal to number of columns. So if the rank of A is n, that must be also that we have the nullity of A is 0, because n plus 0 is equal to n. And these are true if and only if the orthogonal complement of the null space of A is Rn. Why? Because the orthogonal complement of A is just the row space of A, and the orthogonal complement of the row space of A, which is the same as the null space of A, is the set just containing the 0 vector. If you know that one of these statements is true, then you know that the other 16 are also true. If you know that one of these statements is false, then immediately you know that the other 16 statements are false. Our third topic for today's lesson is the topic of linear transformations. What is a linear transformation? Well, let V and W be vector spaces. A function t from the vector space V to the vector space W is called a linear transformation if and only if these two rules are satisfied for all vectors u and v and for all numbers k, for all scalars k. We must have that t of u plus v is t of u plus t of v, and anytime we have a number k inside the function, we must be able to take it outside. T of ku must be the same as kt of u. There's a special case where the vectors v and w are the same. If v and w are the same vector space, then we have a linear transformation from v to v. And in this special case, instead of saying linear transformation, we say linear operator. Now, let me remark that I've tried to avoid mentioning linear transformations up to now because we haven't needed to talk about them yet. Your textbook does things in a different order. If you've been reading your textbook from the start, you would have seen these already in section 1.8. So some of the topics in today's lesson you will have already read about. I also want to remark that this word transformation, it's just another word for function. Don't worry about the word transformation. It just means function. In the phrase linear transformation, the important word is linear. Linear means these two things in the yellow box at the top. If we combine these two rules in the yellow box, we could write that T of K1 V1 plus K2 V2. If we have a linear transformation, anytime we have a plus, it means we can split the function at the plus. And anytime we have some numbers, we can take the numbers outside. So this is going to be the same as K1 T of V1 plus K2 of T of V2. Or more generally, if we had R vectors and R scalars, T of K1 V1 plus K2 V2 plus dot 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 plus KR VR must be the same as K1 T of V1 plus K2 T of V2 plus dot 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 plus KR T of VR. Now we're going to be talking about linear transformations or linear functions. This course is about a type of mathematics called linear algebra. We've been talking about linear equations and linear systems. Now it's time to talk about linear functions or linear transformations or linear operators. Theorem: if T is a linear transformation, then T of the zero vector is equal to the zero vector. And let's prove this. Let's prove it by saying let U be any vector, and then we're going to use the fact that the number 0 multiplied by U is equal to the zero vector. So T of the zero vector is going to be T of the number 0 multiplied by U. But because T is a linear transformation, the number 0 we can take outside of the function, so that we get the number 0 multiplied by TU. TU is a vector, multiply a vector by the number 0, we get the 0 vector. So that's it, that's the whole proof. This is another important idea to remember. Anytime we have a linear transformation, T maps 0 to 0. Or if you have a function which does not map 0 to 0, then immediately you know that it's not linear. The first example of a linear transformation I'm going to give is a matrix transformation. Let's suppose A is an M by N matrix, and then we can define a function from Rn to Rm by this. T subscript A of x, our function, is going to be equal to Ax, A multiplied by x. And that's why it's from Rn, because we need an n-dimensional vector here if A is an M by N matrix, and then after we multiply our M by N matrix by our n-dimensional vector, Ax is going to be in Rm. Now, if U and V are any vectors, and if K is any number, then we can say TA of U plus V, that means A multiplied by U plus V. But we know from our study of matrices that that's just the same as AU plus AV. So we get TAU plus TAV. And for the same reason, TA of KU, which is A multiplied by KU, we know if we have a number here, that's the same as K multiplied by AU, or just K multiplied by TA of U. So that's the two conditions in the yellow box satisfied. This function is linear. TA is a linear function or a linear transformation. Functions like this are called matrix transformations. Let V and W be any two vector spaces, and I want to define a function from V W by the formula T of V is equal to the 0 vector for every vector V. Does this satisfy the two rules in the yellow box? Yes, because TU plus V is the 0 vector and TU plus TV is also the 0 vector. T of KU is the 0 vector because T maps every vector to the 0 vector, and KTU is also 0. So we satisfy both of the rules in the yellow box at the top. Therefore, this function is a linear function. This linear function is called the zero transformation. Another example is the identity operator. Let me remind you, operator means our two vector spaces are the same. We map from V to the same vector space, V. So let V be any vector space. The operator I from V to V defined by I of V is equal to V is called the identity operator on V. I'm going to leave it for you to prove that I satisfies the two equations, the two rules in the yellow box at the top. So in other words, I'm leaving it for you to prove that this function I is linear. Let's talk about a linear transformation from Pn to Pn plus 1. What's Pn? Pn is the vector space of polynomials of degree n or less. So it's polynomials which look like a0 plus a1x plus dot 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 plus anx to the power n. And p to the power n plus 1 is then the polynomials of degree n plus 1 or less. We're going to define a function t from Pn to Pn plus 1 by T of P is equal to x multiplied by P. So in other words, we take our polynomial P and we multiply it by x. So A0 becomes A0x, A1x becomes A1x squared, all of the way up to ANXN, multiply it by x, and we get ANX to the power n plus 1. This function is a linear transformation because x multiplied by P1 plus P2 is the same as x multiplied by P1 plus x multiplied by P2. And x multiplied by Kp is, of course, the same as k multiplied by xp. So that proves that this is a linear transformation. We'll come back to talking about this one later. Let's talk about the vector space of n by n matrices. And I like to write this as r to the power n by n, but some books write this as m subscript nn. There's two functions here, t1 and t2. First question is t1 from Rn by n to Rn by n given by t1 of A equal to the transpose of A linear? In other words, if we take the transpose of a matrix, is that a linear transformation? Or linear operator, I should say, because the domain and the target are the same vector space. And then question 2, T2 maps from Rn by n to the real numbers, and T2 of A is equal to the determinant of A. Is that a linear transformation? Let's answer question 1 first of all. T1 of A plus B, or A plus B transpose, we know is the same as A transpose plus B transpose. So that's T1A plus T1B. And we also know that the transpose of Ka is K multiplied by the transpose of A. So the answer is yes. T1, oh, there's a typo here. This should be T1. And sorry, this should be T1 as well. The answer is yes. T1 is a linear operator. What about T2? Is the determinant a linear transformation? Well, in lecture 4, we've seen that the determinant of Ka is equal to k to the power n multiplied by the determinant of A. So T2 of Ka is k to the power n T2 of A. As long as n is 2 or bigger, we do not have that T2 Ka is k T2A. So the answer is no, as long as n is bigger than 2. As long as n is greater than or equal to 2, the determinant of A is not a linear transformation. Now, remember, linear transformations always have T of 0 is equal to 0. For example, let's suppose B is a non-zero vector in R2, and then we're going to define a function, T from R2 to R2, by T of x is equal to x plus B. Is this function linear? Is it a linear operator? The answer is no. Why? Because T of 0 is not 0. Another example. The derivative or the differential operator on C1, that's the vector space of functions which are differentiable and have continuous derivative, mapping to the vector space of all functions is a linear operator. Why? Because we have the sum rule for derivatives and we have the constant multiple rule for derivatives. We remember these from Calculus 1. So ddx is a linear, oh, I should say a linear transformation. Linear transformation because we have two different vector spaces. Let's talk briefly about finding linear transformations from images of basis vectors. That's something that we'll talk more about next week. Let's suppose T from V to W is a linear transformation where V is finite dimensional. Let's suppose S is a basis for V, then the image of any vector V can be written like this. T of V is C1 T of V1 plus C2 T of V2, etc., where V is equal to C1 V1 plus C2 V2, etc. And this, because this took a little bit longer than I expected, let's take a break at this point. Let's take a 10-minute break. And we will continue at 3:05. And let's continue. I have a couple of examples from the book, from a book. Consider the basis S, which is v1, v2, and v3 for R3, where v is the vector 1, 1, 1, v2 is the vector 1, 1, 0, and v3 is the vector 1, 0, 0. Let T be the linear transformation which maps v1 to 1, 0, v2 to 2, minus 1, and t3 to 4, 3. Find a formula for T and then use that formula to compute T of 2, minus 3, 5. So the first thing to do is to find the coordinates of a vector with respect to this basis. So in other words, we want to find C1 and C2 and C3 such that this equation is true. So we want to find C1 plus C2 plus C3 equal to x1, C1 plus C2 equal to x2, and C1 equal to x3. So in other words, every vector can be written as, after we found this, x3 multiplied by v1 plus x2 minus x3 multiplied by v2 plus x1 minus x2 multiplied by v3. And therefore, t of x1 plus x2 plus x3 is x3 multiplied by t of v1 plus x2 minus x3 multiplied by t of v2 plus x1 minus x2 multiplied by t of v3. All I'm doing is I'm taking this formula for x, and then I'm taking t of each vector. But the question told us that t of v1 is 1, 0, t of v2 is 2, minus 1, and t of v3 is 4, 3. So that gives us our formula for t, and then we're asked to calculate t of 2, minus 3, 5. Just put the numbers in and we get our answer. Let's talk about kernel and range. Let's suppose T from V to W is that linear transformation. Then the set of vectors in V which T maps to 0 is called the kernel of T. And we denote this by KER of T. So that means the kernel of T is all of the vectors V in capital V such that T of V is equal to the 0 vector. The set of all vectors in W, that's in the target of our T, that are images under T of at least one vector in V, is called the range of T, and it's denoted by R of T. So R of T is the vectors in W such that there exists V in V such that T of V is in W. This is the same idea as we know from Calculus 1, when we studied range of real valued functions in Calculus 1. Same idea here. Now, if we have a matrix transformation, then the kernel of TA, that's all of the vectors which are mapped to 0, that's the same as the null space of A. And the range of TA is the same as the column space of A. I'll leave the second one for you to think about. If we have the 0 transformation, that's the transformation which maps every vector to 0. Well, if every vector is mapping to 0, then the set of vectors which map to 0 is the whole vector space V. And what is the range of the T? That's just the 0 vector, because every vector is mapped to 0. The identity operator next. Let I be the identity operator. That's the operator which maps every vector V to itself. I of V is V. But then every vector in V is the image of some vector V, because it's the image of itself. T of V is equal to V. So the range of I must be all of V. Which vectors map to 0? only 0 is mapped to 0 because every vector is mapped to itself. So the set of vectors which map to 0 is just the set containing the 0 vector. Another example. Let's suppose T from R3. R3 is orthogonal projection onto the xy plane. In other words, T is the function which maps Tx z to T to x, y, 0. X goes to x, y goes to y, and z goes to 0. I want to start by finding the kernel of T. Kernel means the vectors which map to 0. So we're trying to find the x, y, and z such that T of x, y, and z is equal to 0, 0, 0. But our formula is that T of x, y, z is x, y, 0. So we're trying to find the x, y, and z so that x, y, 0 is equal to 0, 0, 0. So x must be 0, y must be 0, and z can be any number. That means the kernel of T is the space containing all of the vectors of the form 0, 0, z. What's the range of T? It's going to be the set of points of the form x, y, 0. So in terms of pictures, the kernel of T, when we squash everything down onto the xy plane, which vectors get squashed down onto 0, 0, 0? The z-axis. And what is the range of T? If we squash the whole of three-dimensional space down onto a plane, we get the plane. We get the entire xy plane. What is the kernel and the range of a rotation? Let's suppose we have R2 and every vector v, what we're going to do is we're going to rotate it by an angle of theta so that we get a new vector, T of v. Because every vector in the xy plane can be rotated onto by some vector, that means that the range of T is going to be all of R2. And which vectors get rotated onto 0? The only vector which gets rotated onto 0 is 0. So the kernel of T must be the set containing only the 0 vector. Let's talk briefly about properties of the kernel and the range. These are both subspaces. The kernel of T, that's the vectors in V which map to 0. This is a subspace of V because our function is linear. So if U and V both map to 0, T of U plus V maps to 0 plus 0, which is 0. And the range of T, that's the vectors in W which are mapped onto, that's also a subspace. This time it's a subspace of W. Rank and nullity of linear transformations. Let's suppose T is a linear transformation from V to W. If the range of T is finite dimensional, then its dimension is called the rank of T. If the kernel of T is finite dimensional, then its dimension is called the nullity of T. And if we have a matrix transformation, that's the same as the rank of the matrix and the nullity of the matrix. If T is a linear transformation from a finite dimensional vector space V to a vector space W, W can be a finite dimensional or infinite dimensional, doesn't matter, but we need the domain V to be finite dimensional. then the range of T is finite dimensional. In other words, the rank of T is finite. And we have the equation rank of T plus nullity of T is equal to the dimension of V. So same type of same equation, almost the same equation that we had before when we were looking at matrices. Same idea. Rank plus nullity is always equal to a number. For matrices, it was equal to the number of columns. For linear transformations, it's equal to the dimension of the domain. Our fourth topic is the idea of composition of two transformations and inverse transformations. One-to-one and onto, you've seen before in Mathematics 1, I think, in calculus. If T is a linear transformation from a vector space V to a vector space W, then T is said to be one-to-one if T maps distinct vectors in V into distinct vectors in W. So in other words, if any time we have two different vectors in V, they need to map to different vectors in W. If we don't have that, if, for example, two different vectors, sorry, not those two, two different vectors map to the same vector in W, then it's not one-to-one. And onto, T is said to be onto if every vector in W is the image of at least one vector in V. So in other words, onto means that the range of T is the same as W. The range of T is all of W. If the range of T is smaller than W, then it's not onto. If T is a linear transformation, then the following statements are equivalent. Statement 1, T is one-to-one. Statement 2, the kernel of T is the set containing just the zero vector. I want to prove this theorem. First, I'm going to prove it in the forward direction. If 1 is true, then 2 is true. So in other words, we're going to start by supposing that T is 1 by 1, and we're going to prove that the kernel of T must therefore be the set containing only the zero vector. And we're going to do this using the fact that for a linear transformation, we always have T of 0 is equal to 0. We're going to suppose that T is one-to-one. So we're going to suppose that 0 is the only vector which maps to 0. Well, if it's the only vector which maps to 0, then the set of vectors which map to 0 is just a set containing the 0 vector. Now let's prove it in the opposite direction. Let's prove that 1 is implied by 2, or to say it another way, prove that 2 implies 1. We're going to start by supposing that the kernel of T is a set containing only the 0 vector, and we're going to prove that T is one-to-one. Let U and V be two different vectors in our vector space V, and if they're different vectors, then U minus V is not the 0 vector. And if the kernel of T is equal to the set containing only 0, and if U minus V is not 0, then U minus V does not map to 0. But if that's true, then T of U minus T of V, or T of U minus V, is not the 0 vector, and that then implies that T of U is not equal to T of V. So therefore, T is one-to-one. If our vector spaces V and W are both finite dimensional vector spaces with the same dimension, then we can go further. If T is a linear transformation, then the following three statements are equivalent. T is 1-to-1. Statement 2, kernel of T is the set containing only 0. We've just proved that 1 and 2 must be equivalent. But now we have a new statement, statement 3. T is onto. In other words, R of T, the range of T, is the whole of W. So for example, let's talk about matrix transformations. Next, consider TA from Rn to Rm. TA of X is AX, where A is an M by N matrix. If M is less than N, then immediately we know that TA is not 1-to-1. If M is greater than N, then TA is not onto. And if M is equal to N, so in other words, the dimension of the domain is the same as the dimension of the target. TA is both 1-to-1 and onto if and only if A is an invertible matrix. I'm not going to prove these. I'm going to leave these three things for you to think about. Let's think about the linear transformation from P3 to R4, which maps the polynomial A plus BX plus CX squared plus DX cubed to the vector A, B, C, D. This linear transformation is both 1-to-1 and onto because the kernel of T1 is equal to the set containing only 0. The previous theorem said if our domain and our target are both finite dimensional vector spaces of the same dimension, which is what we have here, 4-dimensional vector spaces, and if you know that the kernel of your linear transformation is the set containing only 0, then it's both 1-to-1 and onto. Why is the kernel of T1 equal to the set containing only 0? That fact I'm going to leave for you to prove. Another example. Let's talk about the linear transformation T2, which maps R2 by 2, that's the vector space of all 2 by 2 matrices, to R4. And it maps the matrix ABCD to the vector ABCD. This is also 1-to-1 and onto because the kernel of this linear transformation is the set containing only 0. Why is it the set containing only 0? I leave that for you to prove. For example, let T be the linear transformation from Pn to Pn plus 1, which takes a polynomial P and multiplies it by X. We looked at this one earlier. We can say that if P and Q are different polynomials, then XP and XQ are also different polynomials. That proves that T is 1-to-1. However, T is not onto. I've written because all images under T have a 0 constant term. In other words, if we, for example, we did T of 1 plus X, we're going to get X plus X squared. Actually, we're going to get 0 plus X squared. Anytime we do this, we're always going to get 0 constant term first. So in other words, it's not possible to get polynomials which don't have a 0 constant term. In particular, it's not possible to find a polynomial P such that XP is equal to 1. So it's not onto. differential transformation, ddx, is not one-to-one. Why? Because the derivative of x squared is the same as the derivative of x squared plus 1. Let's talk about compositions of linear transformations. Let's suppose T1 and T2 are both linear transformations. T1 mapping from U to V and T2 mapping from V to W, where U, V, and W are vector spaces. Then the composition of T2 with T1, T2 circled T1, means first we do T1 and then we do T2 of T1 of the vector. So again, same idea that we know from calculus, but now for transformations between vector spaces. If T1 and T2 are linear transformations, then T2 composed T1 is also a linear transformation. I'm not going to prove this, I'll leave this for you. Two examples. First example, let's suppose T1 maps from P1 to P2. So this is polynomials. I would write this as my special bold P1. And P2 is polynomials of degree 2 or less. And T2 maps from P2 to P2. Let's suppose these are linear transformations given by these formulae. T1 is the one we looked at before. We take a polynomial and we multiply it by x. And T2 takes a polynomial, p at x, and it replaces it by p of 2x plus 4. Then we can do the composition, T2 composed with T1. That's T2 of T1 of P, so T2 of xp. We take x px, and then we replace every x by 2x plus 4. So instead of x, we have 2x plus 4 multiplied by p of. Instead of p of x, it's p of 2x plus 4. And another example. Let's suppose T is any linear operator, and let's suppose I is the identity operator. Operator means that the domain and the target are the same vector space. Then for all vectors in V, T composed of I is the same as T. I composed of T is the same as T. So just like when we were doing matrices, we can multiply a matrix by the identity operator and just got A. We have the identity operator. T composed of I is T. I composed of T is also T. Inverse linear transformations. If T is a linear transformation, then its inverse is also a linear transformation. I think I've missed a word here. There should be one-to-one here. If T is a one-to-one linear transformation, and its inverse with domain range of T is also a linear transformation. For example, the linear transformation that we've been looking at before, T from Pn to Pn plus 1, which takes a polynomial P and it multiplies it by x. We've seen that this is one-to-one, but not onto. Because it's one-to-one, it has an inverse. And then from this inverse, we can write down its formula. What is the opposite of multiplying a polynomial by x? The opposite is dividing it by x. So T inverse maps C0x plus C1x squared plus dot 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 plus Cnx to the power n plus 1 to C0 plus C1x plus dot 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 plus Cnx to the power n. And one more theorem. If T1 and T2 are one-to-one linear transformations, then T2 composed of T1 is also one-to-one. That means it has an inverse, and its inverse is given by T2 composed with T1 inverse is equal to T1 inverse composed with T2 inverse. Now, remember when we did matrices, what is the inverse of AB? Remember, it's B inverse, A inverse. We swap the order of A and B, that's exactly what we're doing here. Swap the order of T1 and T2 and then do the inverse of each one. And that brings me to the final topic of today's lesson. I want to talk about isomorphisms. A linear transformation which is both one-to-one and onto is called an isomorphism. So isomorphism means three things. It means linear, and isomorphism means one-to-one, and isomorphism means onto. If there exists an isomorphism between two vector spaces V and W, then we say that V and W are isomorphic. And I want to remark that if T is an isomorphism, then its inverse, it has an inverse because it's one-to-one, its inverse is also an isomorphism. I'm going to leave this for you to prove. If T is linear and one-to-one and onto, then its inverse is also linear and one-to-one and onto. Now, what does isomorphic really mean? Well, think about this one. T mapping between P2 and R3. T is going to map the polynomial A0 plus A1x plus A2x squared to the vector A0, A1, A2, and T inverse maps back again. On the left, we've got a polynomial function. On the right, we have a vector. But the numbers are the same. A0, A1, and A2 we have on both the left and on the right. That means the behavior under vector addition and scalar multiplication are also the same. On the left, if we add two polynomials together, we're going to get A0 plus B0 plus A1 plus B1x plus A2 plus B2x squared. And on the right, if we add two vectors together, we're going to get A0 plus B0 in the first position, and we're going to get A1 plus B1 in the second position, and we're going to get A2 plus B3 in the third position. Or if we multiply it by a number, take a polynomial and multiply it by k, ka0 plus ka1x plus ka2x squared. Take a vector and multiply it by a number k, we get ka0, ka1, ka2. We have the same behavior on the left and on the right. So we can think of P2 and R3 as basically the same. We have an isomorphism between them. These are isomorphic vector spaces. But they behave the same. It's We can think of them as just two different ways of writing the same thing. Isomorphic comes from the Greek language. Morph means form and iso means identical. So it's isomorphic means they have identical form, or they have the same form or same behavior. And that brings me to a very important theorem. Just as hotels could be 3-star hotel, 4-star hotel, 5-star hotel, etc., perhaps we could say the same about theorems. And if that was true, then this would be a 5-star theorem. Every real n-dimensional vector space is isomorphic to Rn. So that's enough. We can think of this as there really only exists one vector space of each finite dimension. But we're just writing them in different ways. P2 is really just a different way of thinking about R3, for example. Another theorem. Let's suppose that S is a basis for a vector space V. Then the coordinate map, that's the map which takes any vector u in our vector space V, and it gives us the coordinate vector of u with respect to S. This is an isomorphism between V and Rn. Here's one, for example. There's another typo here. This should be small x. The linear transformation T, which maps from Pn-1 to Rn. And it does the obvious thing. It does what we'd expect. It maps this polynomial a0 plus a1x, etc., to the vector a0, a1, a2, etc. This is an isomorphism, and this is called the natural isomorphism between these two vector spaces. Anytime we write down isomorphism, and it's the most obvious one that we can think about, we call it the natural isomorphism. Or we could have the natural isomorphism between R2 by 2 and R4. What's the obvious vector to map ABCD to? We map it to the vector ABCD. This function is called the natural isomorphism between R2 by 2 and R4. What can we use isomorphisms for? Well, for example, are the following polynomials linearly independent? These are polynomials of degree 5. So these all exist in P5, the vector space of polynomials of degree 5 or less. But P5 is isomorphic to R6. Instead of thinking about polynomials of degree 5 or less, we can think about vectors in R6. The following two questions are equivalent. Are these three polynomials linearly independent? Is the same as asking, are these three vectors linearly independent? And an equivalent question is the row space of the following matrix three-dimensional? Are the rows of this matrix linearly independent? I'm going to leave it for you to check that A is row equivalent to this one. And then we can see that the answer is no. There's only two pivots here. So the row space is two-dimensional. That means these three row vectors are not linearly independent. So therefore, the three polynomials are not linearly independent. And on the final slide of today's lesson, I'm going back to a past exam paper. This is an exam from the 5th of December 2018. Part A, we haven't talked about yet. Part A is about the matrix representation of a linear transformation. But I haven't done that yet. I'm going to do that next week. So let's instead look at Part B. Define T from P2 to R2 by T of P is equal to P of 0, P of 1. So this is evaluating the polynomials at two different points. It's evaluating P at 0 and it's evaluating P at 1 to get a vector in R2. Find a polynomial P in P2 which is a basis for the kernel of T. So let me remind you, what does kernel mean? Kernel is the vectors which map to 0. So all of the polynomials in P2 such that Tp is equal to 0. So we're going to start by saying we want to find all of the polynomials which satisfy that T of P is 0, 0. So we want P of 0 is 0 and we want P of 1 to be 0. What is P of 0 if P is A plus BT plus C T squared? P of 0 is just A and P of 1 is A plus B plus C. So we want to find all of the A, B, C, D such that A is 0 and A plus B plus C is 0. Well, we know how to do that. A must be 0 and B plus C must be 0. So our polynomial must be of the form minus CT plus CT squared. So the kernel of T is the vector space, the subspace of all polynomials of the form minus T plus T squared multiplied by C. And that's the span of minus T plus T squared. So the answer to this question, which was find a polynomial which is a basis for the kernel of T, the answer could be minus T plus T squared. And that is the end of this week's lesson. Next week, as I just said, I'm going to talk about matrices for linear transformations, similarity, and then complex numbers. Are there any questions? It should be until homework 6, unless if I've answered the questions right, because it's just the first 6 lectures, and if I've chosen the homework questions correctly, homework 6 should be based on lecture 6 and homework 7 should be based on lecture 7.